Welcome to Module 5 of our Intermediate Robotics course. In this lesson, we'll explore how accelerometers and gyroscopes work together to help self-balancing robots stay upright. You'll learn how to connect and read data from the MPU-9250 sensor, interpret pitch and roll, and see how this information forms the foundation for advanced robot control. Let's get started. In this step, we'll introduce the MPU-9250 sensor, which is a 9-axis inertial measurement unit, or IMU. It combines an accelerometer, a gyroscope, a magnetometer, and a thermometer in a single chip, making it a powerful tool for robotics projects. The MPU-9250 communicates with our microcontroller using the I2C protocol. I2C stands for Inter-Integrated Circuit, and it's a simple, two-wire communication method. The two wires are called SCL for clock and SD for data. With I2C, we can connect multiple devices to the same two wires, each with its own unique address. For the MPU-9250, the typical I2C address is 0x68 or 0x69, depending on how the sensor's pins are configured. Using I2C, our microcontroller can send commands to the sensor and read back data like acceleration and angular velocity. This makes it easy to integrate the MPU-9250 into our robot and start collecting motion data. Let's start by understanding the accelerometer. In the MPU-9250, the accelerometer measures acceleration along 3 axes, X, Y, and Z. This means it can detect both movement and the force of gravity acting on the robot. When the robot is perfectly upright and still, the accelerometer mainly senses gravity on the Z-axis. But if the robot tilts forward, backward, or to the side, the readings on the X and Y-axis change. By analyzing these values, we can calculate the robot's pitch and roll, basically, how much it's leaning in any direction. This information is crucial for self-balancing robots, because it tells us when the robot is starting to tip over, so we can react and keep it balanced. Now, let's look at the gyroscope. The gyroscope in the MPU-9250 measures angular velocity, or how quickly the robot is rotating around each axis. If the robot starts to fall or turn, the gyroscope detects the speed and direction of that movement. This is especially useful for catching sudden changes, like a quick push or a bump. By combining the gyroscope's data with the accelerometer's tilt information, we get a much clearer picture of the robot's motion. The gyroscope helps us track fast movements and correct for them before the robot loses its balance. Now let's wire up the MPU-9250 sensor to our microcontroller. You'll need to connect 4 main pins: VCC, GND, SCL, and SD. Start by connecting VCC on the sensor to the 3.3V or 5V power pin on your Pico W and GND to ground. Next, connect the SCL pin on the sensor to GPIO1 on the Pico W and the SD pin to GPIO0. With the wiring complete, we can move on to interfacing the sensor in code. We'll use the I2C protocol to communicate. In your MicroPython script, initialize the I2C interface and scan for devices. If everything is connected correctly, you should see the sensor's address, usually 104 or 105, appear in the scan results. This confirms that your Pico W can talk to the MPU-9250. Now you're ready to start reading sensor data and using it in your self-balancing robot project. Now that our sensor is connected, let's start reading data from it and interpreting the results. We want to get the accelerometer and gyroscope values, and then calculate the robot's pitch and roll angles. In our code, we'll first create a class called MPU-9250 Sensor. This class will have methods to read the raw accelerometer and gyroscope data, and to calculate pitch and roll. Let's break this down. We import the necessary modules and set up I2C communication. We create an instance of our sensor class. Inside the loop, we call get_accel_euro to get the latest accelerometer, AX, I, AZ, and gyroscope, GX, GY, GZ, readings. To calculate pitch and roll, we use the math.atten2 function. Pitch tells us how much the robot is tilted forward or backward, and roll tells us how much it's tilted to the side. The formulas convert the raw acceleration values into angles in degrees. We then print out the pitch and roll, along with the gyroscope values. The gyroscope readings show how fast the robot is rotating around each axis, in degrees per second. By running this code, you'll see real-time feedback as you tilt or move the robot. This is the foundation for understanding and controlling the robot's balance. Now let's see the sensor feedback in action. As you hold the robot steady, the values should stabilize. This real-time feedback helps you understand how the robot's orientation and movement are measured, and it's the key to developing a self-balancing system. With our code running, gently tilt the robot forward and backward. Watch how the pitch value increases as you tilt forward and decreases as you tilt back. Try rotating or shaking the robot quickly. The gyroscope readings, GX, GY, and GZ, will spike, indicating the speed and direction of the rotation. That wraps up Module 5. You've learned how to connect and interface the MPU-9250 sensor and how to read and interpret accelerometer and gyroscope data for your self-balancing robot. By observing pitch, roll, and angular velocity, you now have the foundation to understand your robot's movement and orientation in real time. In the next module, we'll use this sensor data to implement control logic and start balancing the robot automatically. If you enjoyed this lesson, don't forget to follow and subscribe to Botronix Labs for more robotics tutorials and updates. Thanks for watching. See you in the next lesson.